Hey, Jordan.
Hi.
Hello. Hey, I'm trying to figure out, there's some other people that need to get on. See if you can do the Q&A. If you can, like, there's a Q&A app. I don't know if you have that. See if you can post anything on the question side.
Wait, Q&A app? What?
Question and answer Q&A app.
On Google Plus.
Yeah.
Okay.
Let me see if I can show you from my.
Oh wait, I got it.
You find it? It's over here on the left-hand side.
Yeah.
Okay.
Whoa.
I'm sorry. I don't like doing that part of it. It's usually not an issue, but okay. So Ari's having a hard time. Let me see if I can figure out how to get him on here. All right. Oops.
All it says for me is ask your audience to submit questions and they will appear. Oh, this is for people that's not in the call.
I think you can do it too, but yes, I think you're right.
Okay.
So, wait, did you get an invitation in your email or something, or how did you?
I just went through Google Plus, like my homepage on Google Plus, and it had the like the event.
Got it.
I went to that and I joined the call through the event, and then also additionally, there should be a notification on like on your homepage that the hangout is happening.
Okay. Good. All right. That helps. All right.
Can you still hear me? Is this working?
Yeah. Yeah. No. You're good. I'm just looking at emails and trying to see if any. Oh. I gotcha. Aria tried to do a video call with me, but it won't work. It means I would have to drop this one.
Oh.
So I'm hoping he figures this out and gets on.
Here, I'll see if I can message him if I can find him.
Okay. There's other people that want to get on. What I want to know is if people can get on. Okay. I'm going to send some links to some people and see if they can.
Here, I think this is the link to the actual page. So another thing that was confusing is on the details for it. It says at 9 p.m.
Oh, it does?
It does.
Oh no! Darn it!
That's why I asked, because.
Yep. Okay.
I remember you saying.
I said 8, and when I set the event, I thought I set 8, but obviously I messed that up.
Because I remember you saying you had something to do at 9, so
yes.
I figured.
Yeah. All right. Well, this will get better and better all the time. And we do have a review. If we have to do a retake on this, we can do a review for that as well. What I need to do is I need to do a practice one. I need to, like, I know what I need to do. I need to have an extra credit opportunity for people to get on and practice this with me.
Okay.
Extra credit tends to draw people out. All right, but what's happening right now is it's actually being broadcast to my YouTube channel.
Oh, okay, you're live streaming. Got you.
Yeah. So can you put any questions in the question section?
No, I don't. I'm not able to. I think it goes directly from the people that are like watching it but aren't in the call.
Really?
Yeah, because it says ask the audience.
Right.
I think that would be the people that aren't in.
Okay. Maybe that's it. Well, I think you're my audience because I'm the host, but maybe I'm wrong. Maybe you're right. Maybe it is that. So hopefully Christy will get on there. Let's see. Christy Cho is trying to get on there. Okay, so I don't know if she's on there. Christy, if you're on this and can see this, If you are on this and can see this, would you please put in a question in that section? Or you can send me another email to say that you've got it. But let's see, okay. All right. Oh, live. Wait, yes, it's live. Oh, Joanne Chung. Oh, nice. Yes. Yay. Okay, good. All right. Well, we've got at least somebody watching from someplace else. So now this is really cool because that people can post. They don't have to be. Everyone can have their own computer then. Everyone could totally be on their own computer. We could do 30 people, and they could put questions on.
Yeah.
And so, currently answering. Darren Chung's talking about something. Anyways, okay, good. And Christy can see it too. Yes. Jordan, you were right. It's the people watching. So now we can put everybody on. Everybody can watch it. We do a hang on here, and there was a button that I could select if I didn't want to make it available to those that are younger than 18, but I didn't, so then everyone can get on there. So I'm very excited. So when you have questions or comments, you can post them up there, and then what I'll do, and if you guys hit +1, then it means more people are interested in the question, and that means it'll go up the scale of importance up to the top. So anyways, and then I select it, I answer that question. When I'm done, I go back and click done, and that question disappears. What can also happen is that as questions go through, they'll be posted on the timeline when it's posted to YouTube, so that if people look at it and be like, oh, that's the question I want to know about, they can click on it to go right to that part in YouTube. So they have to wait like a half an hour to find the question they were waiting for. Or if you want to go back and say, hey, what did Mr. Werner say about that? It's there. So I am very excited about that. So we can start anytime you guys are ready. Jordan, since you're here, you are welcome to ask the questions.
Okay.
And then I know Joanne and Christy are viewing, and maybe somebody else is viewing possibly too. I don't know if I can see that.
I'm trying to help Arya get into the.
Arya, oh yeah, Arya get on. But yeah, so I can again share the things that we're looking at. If I have documents online, on my desktop. So for example, if you guys want to know things about the practice test, if you want to look at something at 7S, if there's something even more you want to see, I might have to dig it out of my files, but it's there. Okay. And then maybe later you guys can help me identify how you got to this. Was it the YouTube link that got you there, or what was it that got you there and able to do that? So we'll figure that out. So Jordan, we've already spent a lot of, like 15 minutes getting this all figured out, which is good. What is it that you would like to know about?
On the worksheet we got during Plus, it had us like name the amount of carbon and hydrogen atoms associated with the PES chart, and I'm confused on how that works.
That was the mass spec. Okay. You're going to have to give me a moment on this then. I'm going to open up my school, my other window, and I think I have a picture. I'll open that one up and share that. It'll take me just a second.
Yeah.
In the meantime, anybody viewing, Christy or Joanne or whoever, if you guys just want to put questions on there, you can do that. My Schoology link is really not moving very fast. And unfortunately, this is not a picture that I would feel comfortable drawing. Wow, this is taking a long time. All right, so this is what we're going to do. Did you look at the practice test already, Jordan?
Yeah.
Did you understand the mass spec section on the practice test?
I don't think I've gotten that far. I've only done the first question of the free response, so I don't think I've gotten it.
You know what we'll do then is I'm going to share the practice test with you, and we're going to look at that.
Okay.
because my Schoology is not opening. It doesn't help very much. Okay. So you can see the practice test, yes?
Yes.
Good. All right. So if I scroll down, it's question number 1 on the free response.
Oh, yeah, I understand that. Okay.
It's the same principle.
Okay.
That the idea that you have your lowest peak in there, your lowest peaks, the ones that are closest to the left side, they are whatever the element is. And for my test, I'm going to tell you what you're dealing with. So in this case, I told you that it's a chlorine molecule. It's 2 chlorines bonded together. So you look at this and you find the peak that's furthest to the left, and it says 35, and you already know that chlorine, you look it up on your periodic table, and its mass, average atomic mass is 35.45. So that means that that lowest peak is 35. That is 1 chlorine atom. Now the molecule is Cl2, which means that when there's just 1 atom, that's a fragment. And so you can identify it as a fragment. You can identify what it consists of. In this case, it's chlorine 35 as the isotope. You'll notice in the answers that I did it in 2 notations. There's the hyphen notation, and there's the nuclear notation. And every piece that comes out of the mass spec has been ionized and is turned into a cation. So you have to put that positive out there. So because chlorine's average atomic mass is 35.45, that means it has some isotopes that are 35 and some that are, let's say, 36 or maybe 37. But let's just say that that's actually a 6 right there, that second peak, which means that up here, 70 is with 2 35s. So then we have a molecule. So we have 2 fragments, and we move up here, and now we have a molecule. And the molecule is the complete form of whatever it is I gave you. And maybe it just has different isotopes that make it up. And so 2 isotopes, piece that comes out of the mass spec has been ionized and is turned into a cation. Positive out there. I think so. Because chlorine's average atomic mass is 35.45, that means it has some 35 or let's say 36 or maybe 37. But let's can you use that? A 6 right there, that second peak, which means that here 7 from here 5s. So then we have a molecule. So we have 2 fragments, and we move up here, and now we have a molecule. Mute. There we go. Okay. All right, I had to mute you, Arya. That's okay. We'll get back to that. Okay, so and maybe it just has different isotopes that make it up. And so don't unmute yourself. Okay, so the peaks. So we have the 2 35s make this the 70. A 35 and the 36 together make a 71, and 2 36s make a 72. Now, it could have been 35 and 37. Like, they could have been different. I mean, I was basically, if you were pretty close to that, you're fine. On the mass spec worksheet that I gave you in class, there is only 1 peak that's the molecule. Everything below that was a fragment. And then you just had to piece together what the carbon and hydrogens. It was kind of like a math problem. Together would have made together they would have made the carbon and hydrogen together would have made whatever that fragment is, and then you just identify it. Now, I won't give you anything too large. It probably will not have that many carbons. I would do 1 carbon. I might do a couple carbons, something like that, but it won't be too crazy on the test. And I have no idea what it will look like, unfortunately. I have no idea what it'll look like on the AP end because they haven't put one out there yet for that.
Okay. And the peak 5, that's supposed to be a molecule, not a fragment, correct?
That's true. Yes, that's correct. I made a typo in that one.
Okay.
Okay.
Hello, can someone hear me?
Yes.
Yep, we got you.
Hey, Arya.
Hey.
So, do you have a question?
Let me look, actually. Hold on. 11.
Number 11 on the multiple choice, yeah?
Yeah.
Okay. The electron configuration of the oxide ion is most similar to the electron configuration of the, well, let's make the oxide ion. Let's make that one first. So I'm going to share my, here it is, my bamboo paper. Okay. So the oxide ion, oops, unless I've forgotten how to do this. Okay. So the oxide ion is an O2 minus. And oxygen has 8 protons and 8 electrons as a neutral thing. So it would be 1s2, 2s2, 2p4, right? But because it's an ion, it gained 2 more electrons.
Mm-hmm.
That becomes 2p6. Okay, because now it has the full octet, right? So let me just, this right here, S and P together make an octet, so this is the full octet. Okay, so now you want to compare to potential other ions. Could be, we've got S2 minus, we've got N3 minus, because that's sulfide, that's nitride. It's O as an oxygen atom, and it is just regular O and just regular N. Okay, so if you look at a periodic table, and I don't have one to show you right now, I could probably help to dig one up. Let me just do that really quick.
Yeah. But I have one too in front of me, so.
That's good. It would probably be better for me to be able to show it online. Let me see if I can just pull up some quick pictures. All right. All right. So I'm going to share that really quick. And so if you look at this, you can see that oxygen and sulfur are in 2 different periods. They're in 2 different rows. So that one definitely won't work. Mm-hmm. Oxygen and sulfur. Oxygen and the oxygen atom, we already said we added 2 electrons to that one. So the oxygen and the oxygen atom couldn't work. The nitrogen atom would not work because it has 1 less electron than the oxygen atom and definitely not as many as the oxygen ion. The only other one that works is the nitrogen ion, nitride, because it also gained 3 electrons to fill its full octet. Okay? So if I go back to the picture that I was drawing, and I was going to draw the sulfide, or the nitride. Oops. I would have 1s2, 2s2. Normally I would stop at 2p3 because it has 7, but remember it's 3 minus, which means it's going to have 3 more, which makes it 6, and that would give this its full octet. And do you guys remember what it's called when 2 atoms have the same electron configuration?
No.
Isn't it
Diamagnetic?
Electronic. There it is.
Okay.
So the answer is the nitride ion.
All right.
Does that make sense?
Yeah, it does, actually. Thank you.
Okay. All right. I have a question from Christy. On worksheet 7S, could you briefly explain the ionization energy in kilojoules per mole charge? I understand how to figure out the multi gases, but from there, I'm confused how to find which group an element is in. Number 12 on worksheet 7S. All right. Well, let's pull that one up. So I should probably select that one because that's the one that I'm working on. Share 7S. Number 12. Okay. So you can see the ionization energies in kilojoules per mole. And we want to find where the biggest jump is. Where does it rise the furthest? And from 700 basically to 1400, that's about double. From about 1400 to 7700, you could almost say that's like a 5-fold increase there. From 7,700 to 10,000. So 7,000 to 10,000 isn't even double. From 10,000 to 13,000 isn't double. And 13 to 17,000 isn't double. So this is the biggest jump from 2 to 3. So wherever the biggest jump is, that is your noble gas. So the third electron being removed is your noble gas. That's what that means. Big jump, big jump, noble gas. And then from there, you have to add electrons to figure out which group it is. So it always works that after you've identified which one the noble gas is, the electron immediately to the left is the alkali metals. And the next one over is the alkaline earth metals. And then if we had kept going, that would have been the third column, the 3A column with boron and aluminum, and we would have worked that direction. So since we started here, we would say that the answer to 12A, in which group would it be found in the alkaline earth metals, because that's where we said that was right here. Explain your answer to 12A. The way we would explain it is to say that if that is the third electron removed, we would say first that the largest jump in ionization energy occurred between the second and third electron being removed. Noble gases have the highest ionization energy, therefore that electron being removed would have the greatest ionization energy change from one to the other. And if you added one electron, that would be the alkali metals, and those ones do not hold them as strongly because there's a lot of shielding, and there's only one electron there, so the number of protons, the effective nuclear charge, is not as strong on it, and so it makes sense that would be the alkali metals. So then if we go this direction, we would just be adding electrons, and then the first column would be the alkaline earth metals. So if I go to the answers, I'm hoping that's kind of what they put, and I'm hoping that my answer makes sense. Let's see what they said, or what Adrian said. Oops, I just shared the same one. Oh, there it is. Where is it? Oh, there we go. So 12A said, it was column 2, which is the alkaline earth metals. The large increase in ionization energy between the second and third values suggests that the third electron is an inner quantum shell, closer to the nucleus with less shielding, therefore experiences a greater attraction nucleus. Well, I don't think Hitz does a very good job of describing it. I mean, he describes it. The big thing is he's describing with the shielding and the attraction based upon the effective nuclear charge, which is what you should always use, effective nuclear charge and shielding. But what he's saying there is an inner quantum shell, so it's a lower energy level. When you add them, so after the noble gas, when you add them, you have to add them to a higher energy level, further from the nucleus, which will have, like he said, less shielding. So that's why it takes less ionization energy, because of the fact that it's further from the nucleus, it has less shielding, and it would be an alkali. Well, it doesn't really. I guess I'm probably going a little bit off the rails here to keep talking about the alkali metals, but he's involving his answers with the shielding. So once you find the noble gas, immediately to the left is group 1, or the alkaline metals. The next one over to the left is the alkaline earth metals. So I'm hoping, Christy, that answered your question. I'm going to select that one as done, but feel free to go back to it and ask for more clarification if there's something that I missed. Okay. Is there another question that I can help with?
Mr. Werner, can you do the second graph on the mass spectrometry worksheet?
The one that I gave you guys in the in class 3+ period?
Yeah.
Okay, I'm having a hard time pulling that one up. My Schoology was not working, was the problem. Oh, it looks like it might be up now. Let me see if I can get it.
If you're having trouble, Mr. Werner, I think I can pull it up.
I think I have it. I think I've got one. Oh, good. It looks like I might have it. Okay. Actually, I think I have it. Let's see if I can share it with you guys. There we go. Okay. So it might be hard to see. I don't know if I can. Oh, there I go. I can make it bigger. Okay. Can you guys see that okay?
Yeah.
Yes.
All right. So on the second graph down here, in this particular instance, I didn't tell you what the substance was, but you know that the peak that is furthest to the left is always a single atom. The peak furthest to the left is always a single atom. So the furthest to the left is a 12. So then you look and see which atom has a mass number of 12. And in this case, that answer is carbon.
Okay.
Now, when you move to the right of that, would be the CH, because 12 plus 1 is 13. Did I tell you anything? No, I don't think you had to figure it out. You knew it had carbon and hydrogen. I guess that was helpful. So 12 plus 1 is 13. If you add one more, you get 14, 15, all the way up to 16. Now at that point, I probably should have put a plus up here too, and I didn't. But these two should have pluses on them because it ionizes everything. So that's a plus. The 17 is really small because I believe that's carbon 13. It's an isotope because you cannot put 5 hydrogens on carbon because it won't go that far. This is a little bit more complex than I would give you. I would knock this peak off. This would not be a part of it. But.
Okay.
So that's how that graph works. Does that kind of explain?
Yeah.
Okay.
Yeah.
Okay. Excellent. Other questions?
I need help with number 2 on worksheet 3A.
Worksheet 3A. Okay, give me a second to open that one up. All right, here we go. Is it opening? Oh, it didn't open. Why didn't it open? Oh, I think it just opened. There we go. It's there. Okay, 3A. And so which number, I'm sorry, which number did you say again?
2.
Number 2. So the lithium ions give a distinctive red flame test. All right, once experiment, the energy of this red light is found to have an energy of 3.06 times 10 to the negative 19th joules. Calculate the wavelength of the light from the lithium ions in nanometers. Not meters, nanometers. Okay. So I'm going to do this on my bamboo paper. All right. Oh, I should probably say what questions these are, huh? So that everybody can reference this. So this was the, oops. This test, multiple choice number 11. All right. And this will be, you know what, I'm just going to make a new page, just in case it takes more time. So this is worksheet 3A, number 2. And so, let's Sorry, I'm having to rearrange it a little bit. Okay. We had an energy that was equal to 3.06 times 10 to the negative 19th joules. Okay. And so we have a formula that energy is equal to Planck's constant times V, right?
Mm-hmm.
And so we're looking for, the eventual thing we're looking for is wavelength. That's the one in question. Okay, so we're going to have to use two equations. The other equation is C is equal to, speed of light is equal to wavelength times frequency. Okay? So we're going to find this. So now there's two ways to do it. One is just to solve for V and then plug in V over here and then solve for lambda. The other way is to do substitution. Do V is equal to C over lambda, put C over lambda over here, and then isolate lambda by itself. Either way is fine. Let's go through the steps. I think an easier way, just an easier way to view it all is if we solve for frequency and then plug frequency in. Frequency, we know it, or this energy, 3.06 times 10 to the negative 19th joules is equal to Planck's constant. I don't suppose you have that in front of you. I can't remember right offhand what that is.
6.63, I think.
6
times 10 to the negative 34.
Yes, times 10 to the negative 34th. And isn't it like joules per second?
I think so.
I think it's joules per second, because then frequency is 1 over second. Or joules times seconds, that's what it is. Joules times seconds. All that times frequency. And if we rearrange that equation, frequency is equal to E divided by H. So frequency is equal to 3.06 times 10 to the negative 19th joules divided by 6.63 times 10 to the negative 34 joules times seconds. Okay? The joules will cancel. And joules will cancel, leaving you with 1 over seconds. And if we plug this in, I'm going to plug it into my calculator that I have here. 3.06 exponent negative 19 divided by 6.63 exponent negative 34. And so my frequency that I come up with is, now we don't want to round yet, so I'm going to include a lot of decimals here. 4.615384 times 10 to the 14th. 10 to the 14th, 1 over seconds is my units. Okay? Now I'm going to use this equation. And in this one, C is equal to 3.00 times 10 to the 8th meters per second. So I'm going to rearrange it so that lambda now is equal to C divided by frequency. So that's equal to 3.00 times 10 to the 8th meters per second divided by 4.615384. And I'm leaving the whole number of my calculator, so it doesn't really matter. 10 to the 14th, 1 over seconds, which means these seconds are going to cancel out. So if I do that, 3, 8 divided by that answer. So I get a wavelength of, wow, 6.50 times 10 to the negative 7th meters. Okay? And we need it in nanometers. Okay? So that means that we have to do one more conversion, 6.50 times 10 to the negative 7th meters. And until you memorize it all, it's just easier to do it like this. 1 meter is equal to 1 times 10 to the 9th nanometers. So that way your meters are going to cancel out. So your nanometers should, just to give you an idea, right here, this times 10 to the negative 7th meters, your answer should be 650. So if I multiply that times 1 exponent 9, I get 650. I mean, I actually did this on my calculator, so I went through all the calculations you guys should have done. 650 nanometers. And that should be the answer. I'm hoping that's what the answer was on the, where's my cursor? There it is. So I'm going to go look at the answer sheet, 3A answers. And this was number 2, right?
Yeah.
And number 2, 650 nanometers. We are good.
And then also, I need help with 3 on the same worksheet.
Okay. All right. We just saw the answer, but that's okay. We'll pretend like we didn't see it. All right. So number 3, which of the following processes will release the greatest amount of energy? So when you release energy, you're dropping from an excited state to a lower energy level, a higher energy to a lower energy level. That's where you release energy. It absorbs energy to go from a lower energy to a higher energy. This is the point at which we talk about the flame test lab, and that electrons absorb energy to jump up to a higher energy level, and then when they drop back down, they release light, and that gives you the color of the flame tests. So the further it drops, the more energy is released. It's sort of like if you took physics and you learned about potential energy. If dropping a ball off a skyscraper, it has so much more potential energy up there. It will have so much more energy once it gets to the ground than a ball that's dropped off the top of your house. So the skyscraper is the 6 to 2. The 6 to 5 would be like you dropped it off one skyscraper onto the next skyscraper, and it was only had like one floor to drop. So that's why an electron falling from the N, where that's the energy level, or the shell, when it's 6, dropping down to 2 is a much greater drop. Does that make sense?
Yes.
Okay. All right. Other questions?
What was the Aufbau principle again?
The Aufbau principle is when you have to put electrons in the lowest energy levels first.
Okay.
So let me go to the where's my bamboo paper?
Wait, Arya,
Yeah.
do you have worksheet 3B? Because it's on the back. This one where you had the all the different configurations and you had to fix them.
Oh yeah.
Yeah.
Oh, okay.
Aufbau would be like here's 1s, here's 2s, here's 2p. And if I started filling with, I put an arrow here, and then I jumped up here, and I put one here, and then I jumped up here, put one up here. Like I'd be violating the Aufbau all over the place because I needed to add the second one in 1s before I could go to the third the second electron before I could go to 2s, or the second electron in 2s before I could go to 2p.
Okay.
Or you might see it like I think in the practice test I just did this. Like okay, you skipped 1s and 2s entirely. That's a violation of the Aufbau principle. It just so happens that it's also the orbital notation for electron that's in the excited state. But that's what happened there.
Okay.
Okay? If you were doing the Pauli exclusion principle, if you have two arrows that both point up, that's a violation of the Pauli exclusion principle.
Okay.
Okay? The last one is Hund's rule, in that you have to put one arrow in each of these before you can add a second one to go down. Okay? If you're going to violate that, you're going to do something like this. You've added a second one to the first orbital before you got one in each orbital. That's a violation of the Hund's rule.
Okay.
So make sure you know Aufbau, Pauli exclusion. and Huns.
Okay.
Also a good time to mention that if you're doing electron configuration of a transition metal, let's say that you are doing, let me pull up my periodic table again. I'm not going to pull it up on the thing, but let's say you're doing titanium. And we're doing noble gas notation because it's just easier. So if you're doing titanium and it has argon, that's the one right above, and then it does 4s2 and then 3d2. Okay? Now, if you're doing the titanium plus, it's going to be argon, and then it's just going to be 3d2. You're going to lose that 4s to make an ion. You lose the s orbitals first because they are further out. Okay? The s and p orbitals are the ones that are doing the bonding. They are the ones that are the valence electrons. They are the ones that fulfill the octet rule. And so they're the first ones to come off when you start forming an ion.
Okay.
Good. All right. Other questions?
So I have a couple of just general questions. On the test, when we're writing electron configurations, does it matter whether we put the d orbital first, or like do you have a preference on that?
Oh, you're saying like if I did argon and then I would 3d2 and then 4s2?
Yeah.
That's okay. That's okay.
Is it okay either way?
Yeah.
Okay.
Both are acceptable. And you'll probably see both because they do both. It's kind of funny. I don't know if they've actually gotten to a set way of doing it, but both are accepted. All right. Other questions?
Wait, I had one question. What are diamagnetic atoms?
Okay. So let's go over here, and this one is I keep forgetting to label them. So diamagnetic versus paramagnetic. Yeah, and I'll abbreviate that because I didn't give myself enough room. So basically, full orbitals are oh, I wanted to make this blue. Now I'm just getting ridiculous, I'm sure. Full orbitals, so a full orbital is diamagnetic. And so this means that it will repel magnets. And this is very few elements are this, okay? Very few. Can you guys guess at which elements? If all their orbitals have to be full in a subshell. So the subshells are S, P, D, and F. If you had to guess, what would be one example of a family that is diamagnetic?
Would helium be one?
Yes, so all the noble gases.
Okay.
Good. What else?
The alkali earth metals?
Yes. Alkaline earth metals. Good.
Okay.
Now you could probably go with the very last column in the transition as well. But you probably won't be given that.
Okay.
Is there a reason only those are diamagnetic, or is that just their properties?
No, it's because they're all full. Like here, let me get a periodic table out here so I can point at it. There it is. Okay, look at the second column. So the earth metals, the alkaline earth metals, that means they have a full s orbital, but nothing is in d or p. So because the s orbital is full, those are all diamagnetic. it's anytime you have only one electron in an orbital. Remember that orbital notation we've done?
Mm-hmm.
Anytime there's just one orbital, then it's paramagnetic. Okay? So this second column are diamagnetic. The zinc, cadmium, mercury, no, I don't know what CN is. Anyways, these ones right here would be paramagnetic, and the noble gases would be paramagnetic. Those three columns are the only three columns you could possibly be asked for diamagnetic. Everything else is paramagnetic. Okay?
Okay.
All right. Now I see that Joanne's asked a couple questions about PES and the Bohr model. So what I'm going to do really quick is I'm going to select her first question. Joanne, I'm assuming you're still watching, and I'm going to share one of our, not the entire screen. It must be on this one. I have a tab. I have a tab open to an Arizona State. Where the heck is it? Oh my goodness.
Come on, Werner.
I know, get with it. Okay, there we go. All right, so I'm going to pick something like sulfur, let's say. Okay? And you can see that there's different energy levels. The one that's the highest up here for sulfur, this one is the 1s2 at the very top. Then we come down. And then it's 2s2, 2p6, we come down again, 3s2, 3p4. The reason that with PES and the Bohr model, why we have to revise the Bohr model is because the Bohr model says that there's only one shell. There's 1, there's 2, and there's 3. What photoelectron spectroscopy shows is that within the second energy level, there are subshells. The Bohr model did not show subshells. So the fact that we have 2 different peaks at 2 different energies shows that we have electrons in subshells. And so we have to revise the Bohr model because it doesn't support the Bohr model. In your handout with the PES, there's a graph in there that has 4s, 4p, 4d, and 4f. That is also an example of why we have to revise the Bohr model, because even within the 4th energy level, there were 4 different subshells that encompass the model of the atom. The Bohr model did not account for all these other energy levels. So it's, you know, we're looking for we're looking for evidence to support or having to revise models. And this is a part of AP now. In AP, we have models that describe some sort of physical characteristic of the universe around us. And then we have data that either supports or revises that. And so going through the process of reasoning of why we can support the model or have to revise the model is something that we're looking for. And in fact, Common Core and Next Generation Science Standards are also looking for that. So they're kind of all being, well, I should say Next Generation Science and Common Core are really close together. And AP College Board is kind of joining them there. So anyways, I'm hoping that answers your question. But if that were a question on the test, that is the wording you will need to use to get the points. So I believe that answers the question. So I'm going to say done to that question and done to the Bohr model. And that comes up. So if you want to do if you want to answer to it, because the questions put like bookmarks on the time for the video. So if you just clicked on the revising the Bohr model, you'll have to go back in time a couple minutes to see the answer because we had 2 questions that were similar. Okay, that takes care of some of those questions. So I have like a couple minutes left, but I'll be back at school early tomorrow morning, and you know, I'm on campus all day. If you guys want to come and ask questions, is there anything I can answer really quick?
I'm good.
Okay, Christy. So on the back of the PES packet, since there's no energy levels given, do we just assume it goes in order from the highest energy? Yes. I'm sorry. So it doesn't show the different energy levels. Like it didn't show the layers kind of like we have on this picture right here. So on that one, you would just go to whatever the highest is, and that's 1s2, and then work your way down in energy from that. So I don't remember if highest energy was to the right or highest energy was to the left. Wherever the highest energy is, you start with 1s2, and then just work your way until you get to the last peak, and then you'll know what your element is. Oops, I probably should have selected that so people would know. I got to get used to this selecting the question thing, so it'll bookmark on that video. So start with the highest energy, go to the lowest energy. The highest energy is always 1s2. So on our picture here, the highest energy level will happen to be the third layer like this. And actually, for my test, I keep using these Arizona, AU, Arizona University. I keep using their graph for this. I don't know exactly how College Board will do it, but hopefully they'll do something similar. But the most important thing is find the highest energy first. All right. Anything else?
Just as like a general question, on the test, are the F orbitals going to be involved?
No, there will be no F orbitals.
Okay.
Like that's a little bit too much.
Okay.
So we'll have half the test will be multiple choice. The other half will be free response. Just like the practice test.
Okay.
All right?
All right.
Okay. Well, great job, guys. Thank you very much for joining me here. And I think I will spread the word. I will offer extra credit maybe at some point. We'll schedule another one maybe over the weekend where everybody can get on. I want to get as many people as possible, so really test this out to see if it'll work so that the next time we do a review, it'll be easier and more people will be able to participate. Sound good?
Yep.
All right.
All right. Thank you, guys. Have a good night, and maybe see you tomorrow if you have more questions.
All right. Thanks for sharing.
Yeah, yay!
Thank you.
All right, you're welcome. All right, see you guys. Good night.
Night.